Okay, 8.2, equilibrium of a uniform rigid body. So this would be our main focus today, and it is actually the most important part in chapter 8. Okay, your assignment is going to use the questions from 8.2. So assignment, if I'm not mistaken, so you're going to have 3 questions, if I'm not mistaken. So one of it is coming from 8.2, this subtopic. So you must know how to calculate, okay, how to do the calculations in this subtopic. So before we proceed to our calculations, we must first understand a few new terms in this chapter. So first one is what we call center of mass. So what does it mean by center of mass? Now, assuming you have an object, okay, now you have an object. So center of mass is the point that we can use to represent the whole body, the equivalent body, okay? So this is what we call center of mass. So it is a point equivalent to a whole body. That's why when we sketch free body diagram, usually we just sketch a point because we use the center of mass in our free body diagram. We use this point to represent the whole body instead of you sketch the whole body out, which is a much more harder compared to just using a point. So why is this so important? Now let's consider if you apply a force on the center of mass, what is going to happen to this object? Well, it's going to move in a straight line. So every time when we solve a question in chapter 4, actually we are assuming we exert the force on the center of mass. That's why our object can move in a linear motions. Now what if? Okay, what if I apply the force at a point other than center of mass? So this is still my object. So I have a, okay, this is still the object, and then I have a center of mass here. And then now I exert a force right beside center of mass. So what is going to happen? Because I exert force at a point other than center of mass, now this object is going to rotate. If the question, it doesn't tell you that the object is being fixed at which point, where is the pivot point, then we assume the center of mass is our pivot point. So you push the object, you exert the force at this point, then it will rotate in the clockwise direction. So now what if, okay, what if I put a fixed point on my object where I'm going to call it a pivot point? So this is my object, okay, now I put a nail at the end A, okay, this is point A, so I nail the object here, I put the nail here, and this point I'm going to call it a pivot point. Okay, pivot point at the same time, it will act as our axis of rotation. So you pin it here, and now we are going to see what happens if you exert the force at the same point as the previous case. Now, because you have a fixed point now, okay, pivot point is a fixed point, now you have a fixed point, you exert the force here, it's not going to rotate in the clockwise direction anymore. Now, it will rotate in the anti-clockwise direction because now the axis of rotations have changed. Just now, without any fixed point, we assume center of mass is our pivot point. Now, with a fixed point here, okay, with a pivot point that I give it, so the axis of rotations will change. Okay, the axis of rotation has now shifted to point A. So when I exert the force on the rod now, it's going to rotate in the anti-clockwise direction. So pivot point is very, very important in this subtopic because it is acting as our axis of rotation. Okay, so the magnitude of torque. So in order to determine, to find out whether an object is easy to rotate or not, we use torque. So torque, it tells us the tendency of an object to rotate, whether it is easy to rotate or it is hard to rotate. So the higher the value means the easier the object wants to rotate. Okay, it is easier for the object to rotate. So torque equals to Fd. The magnitude of torque is defined as the magnitude of force times the lever arm. What is lever arm? You look at this diagram. Lever arm is the point from the axis of rotation until the lines of action. So what is the line of action? The line of action is the line that is overlapping with the lines of force, with the force vector. So provided if you exert the force on the door at an angle, as shown in the diagram, so this will be the vector, the force vector. In this first vector, you just extrapolate the line, okay? Basically, you just have to extrapolate it, or you just draw a dotted line on it, okay? And then you extended the line, make it longer. Okay, so after that, what you're going to do, you're going to draw a line from the axis of rotation to the line of action, and the angle between the line of action and this new line, this red color line, must be 90 degrees. Okay, so this is the condition to draw the line for lever arm. The line for lever arm is always perpendicular to the line of action, and it always passes through the axis of rotation. So this is D. Okay, this is the lever arm. So lever arm is the distance between the line of action and the axis of rotation, measured on the line that is perpendicular to both of them. Okay. Okay, now, in our calculations, we seldom use D. Okay, we seldom use D. Why? Because D is quite hard to measure. It is quite impossible to ask you to draw D in your exam, right? So what are we going to use? If you look at this diagram once again, D and F is form a 90 degree. Meaning that the object now, this door now is acting as the hypotenuse of the triangle. So you have a right angle triangle now. So if you don't want to use D, actually you can use R in your calculation. So based on this triangle, it tells us that D is equal to R sine theta. Okay, so you can replace the equations with R sine theta. So torque equals to FD, and at the same time is equals to R sine theta. Okay, and if you recall what we have learned in chapter 1, R sine theta actually is a form of cross product. So in some books, they will define the torque as R cross F. Remember, the sequence is R cross F, not F cross R. This is very important. Why? Because you're going to use it to determine the direction of torque after this. So the sequence must be correct. Okay, the sequence must be correct. It must be R first, R cross F. So first, acting at different angles. Just now we have equation torque equals to F R sine theta. Okay, so if we have an angle, then we can use it. But what happens if you apply the force at different positions? For example, now, you apply a force that is perpendicular to the door. Okay, basically you just push it. So if the angles between force and R is 90 degrees, then we have a maximum torque. Why? Because sine theta gives you 1. Okay, sine theta gives you 1. Therefore, you are going to gain maximum torque. Now, what if you apply the force parallel to the door, parallel to the R radius? So in this case, we have angle 0 degrees. If angle is equal to 0, meaning that sine theta is also equal to 0. Therefore, no torque. The door definitely won't rotate, right? If you exert the force in this direction. Okay? And then, what if you exert a force at the axis of rotation? So try to think now, if you push the door at its hinge, door hinge, will it rotate? Of course not. You can try it in your room, actually. So in these two examples, torque is equal to 0, meaning that this object, it won't rotate at all. Okay? So the door is, you can open it easily if you apply a force that is perpendicular to the door. But if you apply the force that is parallel to the door, or that is on the axis of rotation on the door hinge, then you won't be able to open the door. Okay, so you can try it out by yourself, and you can see whether it's true or not. But you use the door in your room as an example. Try to push the door at different positions. Then you feel that at some point it's harder to rotate, and at some point it's easier to rotate. Why? Because torque depends on the R, the part that you apply force. Okay, so torque kamu kalau nak tahu dia besar atau kecil, actually senang saja. Kamu cuba dengan pintu sendiri. Okay, torque equals to FR sin theta. Kalau kamu tekan dia pada 90 degree di posisi yang berlainan, actually kamu akan rasa tahap kesukaran yang berlainan. Okay, kalau kamu tolak pintu dekat pada door hinge, yaitu axis of rotation dia, akan jadi susah nak buka. Sebab torque dia kecil disebabkan R kecil. Kalau kamu tolak di tengah-tengah, dia senang sikit. Kalau kamu tekan di hujung, dia memang sangat senang buka. Okay, that's why kita buat doorknob dekat hujung. Sebab kalau buat doorknob dekat hujung, Anda tambah R dia. Bila tambah R dia, pintu jadi senang buka. So SI unit for torque is Newton meter. Okay, because FR sin theta, it doesn't have any unit. So FR, force and radius, so we have Newton meter here. And then the sign conventions, this is very, very important. You have to know how to determine sign conventions in this subtopic. So to show the directions of rotation, okay, the sign convention, it tells you the directions of rotation. So if your object is rotated anti-clockwise, then torque would be a negative value in the clockwise direction, sorry. So if the rotational motion is clockwise direction, then it is a negative value. So what does it mean by clockwise? In case you don't know what is a clockwise direction, this is the clockwise direction. Okay? It follows the directions of a clock. That's why we call it clockwise direction. So in this case, you're going to have a negative torque. Then the value is positive if the rotational motion is anti-clockwise. So this is your object. If it rotates in the anti-clockwise direction, okay, against the directions of a clock, so we call it anti-clockwise, then you are going to have a positive torque. So torque is a vector. Okay, so the direction of the torque is always parallel to the axis of rotation. Same as angular velocity, the direction of the rotation, it doesn't represent the directions of torque. Okay, the plus minus sign, it just tells you whether it is clockwise or anti-clockwise. But in order to determine the directions of torque, we need to use right-hand rule. Okay, this right-hand rule is a right-hand rule that you have learned in chapter 1. Okay, when you have A cross B equals to C, first your 4 fingers will be pointing towards the directions of the first vector, which is A, right? And then you curl your fingers towards the second vector, which is B, and thumbs represent the result, which is vector C. That is what we have learned in chapter 1. So in this case, in this chapter, we are just going to apply it. So use your right hand, 4 fingers, you point it towards the directions of R, the radius. So the directions of R, radius, we always let it start from axis to the edge. Okay, directions untuk R bermula dari axis of rotation, menghala ke dia punya sisi, dia punya tepi. So R coming from axis towards the edge of the object. So now your 4 fingers point towards R, and then you curl the fingers towards the directions of the force. Okay, so if your object is rotated in the anti-clockwise direction, definitely your force is going to point towards the anti-clockwise directions. So R and then curl it towards the directions of rotation. And thumbs represent the directions of torque. Okay, thumbs represent the directions of torque. So basically, you just have to recall what you have learned in your chapter 1, right-hand rule. So if you forgot how to find the directions already, you can refer to the notes from chapter 1. Okay, now, before we proceed to the calculations, we are going to recall what does it mean by rigid body. Okay, since we are going to calculate the equilibrium on a rigid body. So rigid body is defined as a body, once again, with a definite shape that doesn't change. So that the particles that compose it stay in a fixed positions relative to one another, even though the force is exerted on it. So for example, if you exert a force on the table, the shape won't change. So table is a rigid body. Okay, so liquid is not. So this is a typical example. So particle is a body with negligible dimensions. We assume no dimensions because it's very, very small. And then rigid body is negligible deformations. So what does it mean by negligible deformations? For example, you as a human, so your skin is soft. When you apply a force on your, let's say your hand, the shape, it might change a little bit because when you compress it, okay, your skin is soft, the shape will change a little bit. But the deformation is negligible. Okay, the shape, it won't change a lot. So this one, we consider it, we can call it as a rigid body because it is with negligible deformation. Okay, macam kamu tekan kulit kamu lembut, tekan mungkin dia masuk sedikit sahaja, tapi bila kamu lepas, dia kembali kepada shape asal dia. Okay, so dia takkan tekan, kamu punya tangan jadi V-shape. Tak ada kan? So that one we call it rigid body. So human basically is a rigid body because the object, you as a human, has a negligible deformation. Okay, kecuali kamu punya tangan patah ke kaki patah, itu baru deformations yang obvious. And then non-rigid body, basically you can deform it easily, especially such as a liquid, gas, all those. Okay, we call it non-rigid body because it can be deformed easily. So if a body is in equilibrium, now we want to proceed to our main course, equilibrium. So when you have the term equilibrium, it means that the body is both translational and rotational equilibrium. So it is equilibrium in terms of linear motion, and also it is equilibrium in terms of a rotational motion. So in chapter 4, we have learned that when an object is in equilibrium, total force acting on the object is equal to 0. That is in terms of translational motion, where you analyze the motions of an object based on y component and x component. And in this chapter, we are going to add in another type of equilibrium, which is the rotational equilibrium. Means the object also won't rotate because the torque exerted on the body is in equilibrium. Okay, this is an example. Okay, this is an example. So now we have a diagram. Okay, we have a diagram. The parent is holding a plank wood and the kid is sitting on top of it. So in this case, okay, the object that can be rotated based on the diagram is the plank wood. The axis of rotation is on the mother side. But because the father is holding the plank wood on the other end, this plank wood, it won't rotate. In this case, because the plank wood is not rotate, it stays in a static position, it's stationary, so we say it is equilibrium. So when it's equilibrium, we can conclude that summation F acting on the plank wood is equal to 0. So what does it mean by summation F is equal to 0? The force pointing upwards, which is F1 and F2, cancel out with the force that is pointing downwards, which is the weight of the plank and also the weight of the child. So total force along y-axis is 0, and total force along x-axis is equal to 0. It's very obvious because there is no force on the x-axis. So summation Fx is definitely equal to 0. And then when it is in equilibrium, the total torque is also equal to 0 because it doesn't rotate. Meaning that the clockwise torque and the anti-clockwise torque, they are cancelled with each other. Okay, so how to determine whether it is clockwise or anti-clockwise? It's very simple. Now this is the axis of rotation. You imagine you are holding a pen, okay, at this end. So if you want to determine the directions of rotation, okay, for example, you want to determine the directions of rotation caused by the plank wood, which is the weight of the plank wood. Okay, then you ignore all the other forces. You assume they are not exist. Okay, then you hold this pen at the axis of rotation. So after you hold the pen at axis of rotation, you try to pull it downwards. You pull the pen downwards, and you will see that this plank wood will rotate in the clockwise direction. Now, if you hold the pen at this axis of rotation, and then you pull it down, okay, so it will move in the clockwise direction. So in this case, the torque caused by plank wood is a negative torque. Okay, so when it comes to this father, okay, the father is holding the plank wood. It is he is giving an upward force. So F2 is pointing upwards. Now we want to determine the torque caused by this F2. What are you going to do? Again, you ignore all the other forces. You ignore F1, you ignore W prime, you ignore this mg. And then once again, you hold the pen at this axis of rotation, and then you try to pull it towards the directions of F2, okay? Push it. So when you push it towards the directions of F2, you will see that the pen is actually rotate in the anti-clockwise direction. So in this case, we have an anti-clockwise torque that caused by the father. Okay, so all this torque, okay, the torque caused by F2, mg, and W Planck, they cancel out each other. Therefore, total torque is equal to 0. Then how about F1? F1 is a force exerted on an axis of rotation. Therefore, torque is already equal to 0. You don't even have to determine whether it is positive or negative torque because it is equal to 0. Now, I have one question. How am I going to determine where should I put this W Planck? Right, this plank is a very long object. So how am I going to determine the positions of this weight? Right. In order to determine the positions, we have to understand another term known as center of gravity. It is very similar to the center of mass, but the difference is center of mass is a scalar quantity. It just tells you the point that can be used to represent the object. But when it comes to center of gravity, it tells you the directions of the vector. Where should you put the vector? Okay, where should you put the weight? So the center of gravity of a rigid body is a point at which its weight can be considered to act as when the torque due to the weight is being calculated. So we assume that point, okay, is where all the weights they are gathering together. So for example, if you have a long object, you have a rod, okay? So the center of gravity, okay, if now this is a uniform surface, we have a flat object, the shape, the area on both sides is equal, then we can assume the midway is the center of gravity. Okay, midpoint for a rod is always the center of gravity. So this is where we put the vector for weight. If the object is not uniform, okay, for example, the area on the left-hand side is not equal to the area on the right-hand side, then the center of gravity might shift a little bit. Okay, it might not be at the midpoint. It might shift a little bit. But in this case, in our examples, in our syllabus, most of the time, we have a rod where both area, the area on both ends, they are equal. Okay, so the surface is uniform. So in this case, we can always take the midpoint as the center of gravity, and that is where we will put the directions of weight, okay, the directions of the vector weight. So when you have a sphere object, the center of the sphere is where we use to represent the weight of the object. So weight is coming out from the center of the sphere. But in our case, most of the times we just have a rod, okay. So how are we going to solve questions when it involves a rigid body, okay, especially when it involves a rod? So first you sketch a simple diagram of the system. So it helps you to conceptualize, so it helps you to imagine, okay, how is it going to move? How is it going to rotate if you exert the force on it? And then you sketch a separate free body diagram for each body. What does it mean? We'll look at it later. And then you choose a convenient coordinate axis for each body, and then you construct a table to resolve the force into their components and determine the torque by each force. This one is very similar to chapter 4. Okay, when you solve a Newton's law question, you have to construct a table which consists of X components, Y components, and also the torque. Now you have an additional column in your table. And then you apply the conditions for equilibriums of rigid body. So once again, what is the conditions for equilibrium of a rigid body? So there are two conditions. Summation F equals to 0 and summation torque equals to 0. Only these two equations can be accepted in your exam. Okay, you don't give all the other answers. It won't be accepted in your exam. So the conditions to achieve equilibrium for a rigid body is the total force acting on it is equal to 0, which is summation F equals 0, and the total torque acting on it is equal to 0, which is summation torque equals to 0. Okay, and then the last step, of course, you have to solve the equation. Okay, let's take a diagram just now as an example again. So you have a mommy, you have a daddy, and then you have a boy here. Okay, we are going to construct a diagram for these questions. So the object that can be rotated, that is the first thing that you have to do. You look at the diagram, and then you see which part is acting as our main object. We have 4 objects in the diagram. We have the mommy, we have the daddy, and then we have the boy, and also the plank wood. So which object is our main focus in the question? Of course, the object that can be rotated, which in our case is the plank wood. Okay, it's the plank wood. So the object that can be rotated is the plank wood. So we are going to construct a free body diagram for it. And if you notice now, the force, okay, the force, we applied it at different points along the plank wood. Okay, we are not exerted the force on the center of mass anymore, like chapter 4. Chapter 4, we exert the force on the center of mass. But now, the force is being exerted at different positions, not the center of mass anymore. So in this case, how are you going to draw the free body diagram? You use a long straight line to represent the object. Okay, we don't use a dot anymore because now we have force being exerted at different positions, at a position other than center of mass. So in this case, we use a long line, a straight line to represent my object. Okay, and after you draw a straight line, the most important part is to point out, is to label the pivot point, okay, which is our axis of rotation. So in this case, pivot point is on the left-hand side. So I put a dot here to represent the pivot point. And then you just transfer all the force, okay, all the force vector in the diagram into our free body diagram. So W plank, and then we have F1, and then we have F2, and we have mg. Done. That is the free body diagram, the complete diagram for our questions. Okay, you don't go and sketch the force acting on all the other objects. Remember, when you sketch a free body diagram, you're just going to take into consideration the force acting on this object. Okay, acting on the plank wood only. So one very typical mistake that students make is students like to put a normal here. Why? Because students say the boy is sitting on the plank wood. Then there is a normal force acting on the plank wood, acting on the boy. So, well, if the normal force is acting on the boy but not the plank wood, then you cannot put it in our free body diagram. Normal force, okay, let's see. Where should we put the normal force? So let's look at the other object, boy. So this is a free body diagram for the boy. The boy is an object that comes with a weight, so we have mg, and the normal force is the force that's acting on the boy. So we put it in the free body diagram for the boy, but not for the plank wood, because this normal force is not being exerted on the plank wood. Okay, this normal force, it exists because this boy is sitting on the plank wood. Okay, and this force is acting on the boy. So if you want to sketch a normal force in the diagram, you put it to the boy, you give it to the boy. Okay, but you seldom need this one. Okay, you seldom need this one unless the questions want you to calculate the weight for this boy first. Before you calculate, you solve the question. Otherwise, you don't even need this free body diagram. Okay, the most important free body diagram is the free body diagram for plank wood. So remember, plank wood, when you sketch the free body diagram, you just want to take into consideration the force acting on a plank wood. So we have F1, we have F2, we have W plank, and we have mg. That's it. Okay, and if you need other free body diagram, then you sketch it separately. So that is the second step. Okay, just now I showed you 5 steps, right? Step 1 is a diagram for plank wood. Step 2 is a diagram for all the other non-important objects. So this is a boy. So step number 3, we are going to determine the axis. So usually we'll just take horizontal as x, vertical as y. Okay, we are not going to take the slope as the x component anymore. Okay, remember, we are just going to take the horizontal component and the vertical component as usual. Okay, so floor is an x and then this is a y. So you don't have to follow the slope surface anymore in this chapter 8. So we have the x-axis, we have y-axis, and then after that we are going to determine the sign conventions for the top. So if the force causes the object to rotate in the anti-clockwise direction, then it is a negative top. So if the force causes the object to move in a clockwise direction, then we are going to have a positive top. So after you determine the sign convention for each of them, for every single component in the diagram, you can then apply the two conditions, which is summation f equals to 0 and also summation top equals to 0. The two conditions for equilibrium of a rigid body. So this is a must in our calculations. And then after that, you just construct a table. So now we are going to try an example. Okay, we are going to try an example, see how to solve a question for a rigid body. So this question is a question in your book. Okay, you go to exercise 4, question number 3, page 168. Okay, I give you 2 minutes, go to take your books, and then take a piece of paper, take your stationery, and then let's do these questions together. Okay, you can try to sketch a diagram first, yeah, while waiting for the rest. Okay, now let's start. So a floor line of mass 20 kg. So floor line is this one, okay, the lamp. So this is our floor line. In a part is supported at the end of a 10 kg uniform horizontal beam. So this beam itself is equal to 10 kg. Okay, this beam is 10 kg, and then this light is 20 kg, according to the question. So a cable at an angle 30 degrees with the beam is help to support the light. So this one is a string, is a cable. Okay, we put the cable here to support the light, because maybe without this cable, this beam it won't be able to hold this light. Okay, because it's too heavy. So this string it helps to make it equilibrium to hold the light. So now we have a diagram like this. First thing, we are going to sketch a free body diagram of the beam. Okay, so this question is being very nice to you. Why? Because it tells you what is our main object. So the main object is the beam, which is quite obvious because the only object that can be rotated is the beam if the force is not balanced. So this beam is our main object. So we are going to sketch a free body diagram for it. First, okay, let all be the rotations exist. So this is the diagram. We select the rotation axis first before we sketch the diagram. So I'm going to take usually we take the hinge. Okay, kita ambil tempat yang dia paku ini sebagai kita punya rotation axis. So usually we take this end as a rotation axis. So now we have the beam here. And then we have a rotation axis at the left-hand side. After that, if you look at the diagram, okay, this is the beam. Beam is an object. Once again, every object, it comes with a weight. So we are going to determine where should we put our weight. So let's take this as a starting point. And then the length, okay, we label the length of this object as L. Therefore, weight is always located at half of the length, 0.5 L position. Okay, so this is our WB. So the point, okay, the midpoint of the beam is our center of gravity. And this is where we should put our WB, the weight of the beam. And then we are going to put the weight of the lamp in our diagram. Why? Because it has a mass. So when it is being hanged here, okay, being put it at the ends of the rod, it's going to exert the WL, WL on the object. And then other than these two weights, okay, other than these two forces, we have a cable in our diagram. So every cable comes with a tension. Therefore, we have a tension at an angle 30 degrees above the beam. So now we have three forces. Is that all? Obviously, it's not. Now, if you notice, this beam is in contact with another object, which is a pole. Okay? So this beam is in contact with a pole. Therefore, it should have a reaction force. But reaction force in our case is a bit different than previous chapter. This normal force is not perpendicular to the surface. Why? Because other than the normal force, okay, there is a force that's stopping it from going down, from dropping. So actually, there are two forces acting on a pivot point in our diagram. Okay, a normal force and maybe another frictional force. So in our case, we are going to label it as S. Okay, we are going to label it as S, which is the reaction force at point O. So we don't use normal force, we don't use frictional force. In this part, when you have an object like this, we call it S. Okay, we call it S. So this is a special case when it involves a string here. Okay, when it involves a string here. So as this cable actually is also acting as part of the factor why this normal force is shift direction. Okay, I'll explain it to you when it comes back to the school. Okay, because it's very hard to explain it when you can't see me. So let's all do the rotations exist, and now we have a diagram like this. So we are done with the first part. And then do you need any other diagram in this case? No, I don't think so. So one diagram is more than enough. Now let's see how to construct a table. So first of all, I'm going to choose the axis. So like I told you just now, for questions in chapter 8, you don't have to rotate the XY plane. You just take the horizontal as the x-axis and then vertical as the y-axis. So you're going to construct a table like this. Okay, you're going to construct a table like this. So this is the table where you have force, x component, y component, and then you have torque equals to FD. Okay, torque, the column for torque. So I'm just put the equations here so that you know how to calculate FD. In the exam, actually, you don't have to show this formula. Okay, I'm just putting it here so that you know what is going on. Okay, now let's see how am I going to complete this table. Obviously, the first step, you're going to transfer all of these forces into the table. So I have 4 forces. So WB, WL, T, and S. And then after that, I want to complete the X component. Okay, how to complete the X component? WB. WB is the force that is pointing downwards. So obviously, the X component is equal to 0. WY and WL also the same. WL is pointing downwards. Therefore, the X component is equal to 0. But now for T, the the x is no longer equals to 0. Why? Because t is located in between x and y components. It comes with an angle. So in this case, I have to resolve t. Okay, I have to resolve t in order to get its x component. So this x component, if you look at the diagram, 30 degree is located beside x-axis. Therefore, I'm going to use cos theta for the x component. And if you resolve this t into x and y component, you will see that Tx is pointing to the left. Okay, it's heading to the left. Therefore, we have a negative value. Negative t cos 30 degree. Negative because it's to the left. Cos because it is beside the angle. It has to use the equations, the relationship. Tangent theta equals to sine theta over cos theta. Both are accepted. Okay, both are accepted. Just see you prefer which one. Now let's complete the table for the y components in the table. So WB pointing downwards. Therefore, you have a negative WB, which is negative MBG. For WL, okay, again, it is going down. Therefore, you have a negative sign here. So negative MLG. T, once again, you have to resolve it. So after you resolve it, Ty is going up. Therefore, you have a positive T sine 30 degrees. And then for Sy, since you don't have any information about it, you just leave it as Sy. Okay, now let's come to the most important part in your table, which is the top. So we want to calculate the value first, and then determine whether it is positive or negative. And remember, this top, it has nothing to do with x component and y component. Okay? A very common seen mistake in the exam, students always take the sign conventions, especially for the y component, when they try to complete the table for top. Okay, which is wrong. Top equals to FR sine theta. The F here, this F, it refers to the resultant force. Okay, it doesn't refer to the x components or the y components of the force. It refers to the resultant force. So basically, what do you need to put in here is the first column. You replace the first column, okay, you substitute the values from the first column into here. So for example, top equals to FR sine theta for WB can be written as top equals to WB sine theta. Okay, so this F, you use a symbol from the first column. Okay, so when you try to complete this column, you ignore x and y component. Totally ignore them. Don't have to look at them anymore. So top equals to FR sine theta. F comes from the first column. R is the distance between the axis of rotation until the point of force. Okay. So for example, the first one WB. The R, okay, the distance between axis of rotation until the force is 0.5 L. So I'm going to substitute 0.5 L in the first top. So now what do I have? I have top equals to WB times 0.5 L sine, okay, theta. What is the value for theta? Theta is the angles between R and W and the force. Okay. So just now, like I told you, the directions of R is coming from rotation axis until the edge. So basically, R is along the road, the beam. So R along the beam, WB perpendicular to the beam. So angle between them is 90 degrees. So sine 90 equals to 1, so you don't even have to put it in your table. So after you substitute everything, okay, you will get W 0.5 L. And I put a negative here, it isn't because of the y component. It is because my object is moving in a clockwise direction. If I remove all the other forces, but except WB. So try to imagine you're holding point O, and then you try to pull the object towards the directions of WB. Then your object is going to rotate in the clockwise direction. That's why I have a negative sign here. So negative WB 0.5 L. Okay, so after I write down the equation, I just expand it. Negative MVG times 0.5 L. Okay, so basically you just have to keep repeat the same thing for every single force. So WL negative WLL. Okay, the weight of the line times the distance between the point of the force vector with the rotations axis. The distance in between these 2 points. So we have L here. Negative because once again it is moving in the clockwise direction. And then the top for T. Okay, the top for T. So now as you can see here, I have the T here. Not T cos theta, not T sin theta, but resultant T. So TL sine 30 degree. Okay, this 30 degree exists because of the equations of torque. It is not because of Y component. Okay, so don't get confused. Torque has nothing to do with Y component. Keep that in your mind. It is very, very, very important. Yet every year, got plenty of students make the same mistake. So TL sine 30 degree. This sine 30 degree is because of the equations of torque. It is not because of equations of Y component. So it is positive because if you pull the object towards the directions of T, then the object is going to move in the anti-clockwise direction. So how about the last one? The last one, you don't even have to calculate because the force is being exerted on the axis of rotation. Therefore, it is equal to 0. So done. Now you're complete with the table. So what should you do next? So you're going to apply the 2 conditions for object in equilibrium. The first condition, okay, the first condition is summation F equals to 0. So when summation F equals to 0, it tells us that the total force acting on the object along the X component and the Y component is equals to 0. So summation F equals to 0, and then summation Y also equals to 0. Okay, so I have X0, I have Y0. So 2 0 here. And then what should I put for torque? Same. According to second condition, total torque is also equal to 0. So when you add up all four of them, you're going to get 0. Okay, so that is how you apply the 2 conditions. So now that I have this complete table, I can then proceed to solve my questions. So questions B. Questions B asks you to determine the calculate the tensions in the cable. So if you look at the table, which column can be used to calculate tensions? The first one? No. Why? Because there are 2 unknowns in the first column, in the X component. You have unknown T, you have unknown Fx. If you look at the second column, the Y component column, can you use it? Again, cannot. Why? Because you still have 2 unknowns. Unknown T, unknown Sy. Meaning that you are left with just one choice, okay, which is the column for torque. So the column for torque, you have all of this value, MV, you have it already, the mass for the beam, the mass of the lamp, and the length, you're also given the length, if I'm not mistaken. Even if you don't have the length, don't worry, because you can just cancel it out later on. So you want to calculate T. So you're going to use summation torque equals to 0. You are going to use the columns for torque. So summation torque equals to 0. So you just write down everything. Negative MVG times 0.5 L minus negative and minus MLG times L plus TL sine 30 degree. Rearrange the equations. Okay, we keep T on the left hand side because that is the quantity that we want to calculate. So the rest you just substitute the value. Okay, you have the theta, you have a value 10, 9.81, 20, 9.81. L, you want to substitute the value or not, it's up to you. Why? Because you can cancel out everything actually. Okay, you don't even have to calculate it. So cancel all of the L, and then you have T sine 30 degrees equals to 10 times 9.81 plus 20 times 9.81. Rearrange the equations, you will get T equals to 490 Newton. So that is the answer for question 1. Okay. So next, we want to calculate the force exerted on the beam by the pole, meaning that the question is asking for reaction force. In our case, reaction force is the S. Okay, reaction force is the S. It exists because of the pole. So what am I going to do now? S, okay, if you notice in the table just now, the torque for S is equal to 0, meaning that you cannot use the columns for torque anymore. So how am I going to solve this question then? You can calculate Sx and Sy. So for X component, we have summation Fx equals to 0. Okay, substitute the value for T. You have negative T cos 30 degrees plus Fx. T was determined just now, which is equals to 490 Newton. So Fx equals to 424 Newton. Okay, repeat the same thing for vertical component. So summation Fy equals to 0. T sine 30 degrees plus Sy equals to 0. And we have Sy equals to 49.1 Newton. Okay, so you have Sx, you have Sy. Now we want to determine S, which is the resultant vector. Okay, which is the resultant vector. And because force is a vector, you also have to determine the angle. So you determine the force, you determine the angle. Now that you have X component, and you also have the Y component, then you can proceed to this equation. S equals to square root Sx squared plus Sy squared. So you just put in all of the values, and you'll see that S is equals to 427 Newton. Okay, 427 Newton. So the angle is given by theta equals to tangent negative 1 modulus Sy over Sx. Plug in the value, you will see that theta is equals to 6.61 degrees. Don't forget to describe the position of the angle. But in case if you forgot how to describe it in your exam, you can just draw a diagram like this. Okay, so it is accepted in the exam. Okay, tak semestinya kena describe, okay, above positive x-axis or what. Okay, you can show it by using diagram. So this is your S, vector S, and this is the angle. Okay, so basically, that's all for 8.2. So far, any questions? I'm not going to do 8.3 yet. Okay, I'm not going to do 8.3 yet. I'm just going to stop at 8.2.